My name is Hong. I am the Yuan. I am the Open Data Liaison at New York City Department of Transportation. Thank you for coming to this presentation with MTA and DOT on this book, a presentation on mobility data. We're joined by MTA's Lisa Bay Fiedler and Jaspreet Lau. They will be presenting data and information on buses, subways, and vehicle data. And for DOT, we have Esteban, Doyle, Alec, Bardey, and Smart Seaman that will be presenting on pedestrian counts, vehicle classification counts, and conclude with the citywide mobility survey, which we just released the newest data as of last night. Our colleagues will be putting on any related data sets from open data into the chat as we go. And if you have any questions or comments or insights, feel free to put it in the chat. We would love to have a conversation. And if you want to continue this, we do have our happy hour event at Emily Hall downtown between 5:30 and 7 today. So join us and hopefully continue this conversation. Okay, great. So we're going to kick it off so this is the order of the presentation, and we're going to kick it off with pedestrian counts with Esteban.
Hello, thank you. Hi, everyone. Thank you for joining us today. My name is Esteban Doyle. I'm a senior planner at DOT in our public realm unit. The public realm team really focuses on pedestrians and making our streets more comfortable and improve walkability for pedestrians throughout the city. Today, we'll be giving a very brief presentation on our biannual pedestrian count program and the pedestrian demand map. So why talk about pedestrian counts? I think what's really important to understand that knowing where people are walking and how many people are walking is really important for conversations around design and setting priorities. Historically, pedestrians are often overlooked when it comes to traditional traffic counts and aren't collected in that same way as like vehicles. But it's really important to understand where people are walking, how many people are walking. When we're having conversations around streetscape design, we're often in situations where there are so many different competing needs, whether that is from vehicles, buses, bikes, pedestrians, other like curb uses, and having accurate and comprehensive data of all users just helps better inform those discussions when thinking about how we allocate space on our roadways. And we have our biannual pedestrian count program. This is a program that started back in 2007 and was originally meant as a way to track pedestrian volumes as this proxy for economic activity following the Great Recession in the early 2000s. And since then, we have continued to add additional locations that we are counting. We are at 114 locations across all 5 boroughs. These are mostly on commercial corridors, but we also do include the East River and Harlem River bridges. And we collect those counts once in the fall and once in the spring on a weekday morning, a weekday evening, and then a Saturday midday count. And so with those counts, one of the ways in which we use that data is we calculate what we call the pedestrian volume index. And this is really a sort of a composite score that looks at the average across all the locations for the weekday evening peak. And we compare those volumes back to that original 2007 benchmark. And it's a way to easily see how volumes have changed over time. And you can see that in the early 2010s, there was a lot of growth in pedestrian volumes, but then there was a sort of a big jump down due to the COVID-19 pandemic. We did not collect counts in the early part of 2020, but have since resumed our data collection, and volumes have definitely started to grow back, but we're not quite at those pre-pandemic levels. An important thing to note about this is that of those 114 locations, again, it's not a representative sample of all streets across the city. Again, this is mostly focusing on commercial corridors as well as the bridges. And so it tells part of the story, but not all of the story. And so as I was hinting to, there are a lot of limitations with this data set. It's not a representative sample. It doesn't include residential streets. A lot of the locations are in Midtown Manhattan, which is where we know a lot of people are walking, but we know that many people are walking in all parts of the city. And so we want to think of alternative ways to make sure that we're collecting and counting those pedestrian trips. We also only collect the counts twice a year. And so there is a lot of those counts are then subject to conditions on that particular day, and they can vary quite a lot in between years. And it's also a very labor intensive effort setting up cameras and then doing sort of the manual counting and cataloging of all those counts. And so we are always trying to think of ways to improve our processes to get a better sense of pedestrian volumes across the city and think of other alternative ways. And so another way that we thinking about pedestrian volumes is our pedestrian demand map. This was released a few years ago as part of our overall pedestrian mobility plan. And as I was alluding to, it's not really feasible for us to collect actual pedestrian counts at every street and every location across the city, but we want to make sure that we're having a sense of what pedestrian volumes are across the whole city. And so we developed the pedestrian demand map, which looks at what we call pedestrian generators. So these are different types of land uses, such as parks, schools, large tourist attractions, commercial areas, places that we know that people are traveling to and want to walk to. And so taking all those different generators and mapped across the city, we categorize all the streets in New York into one of 5 categories. From the global, which are the busiest streets, think of a lot of the main avenues in Manhattan, down to a baseline street, which is you can think of as your typical lower density residential street. And with these 5 categories, we have a set of design guidelines for how wide we ideally would want the sidewalk to be. And we are using this demand map as a way to guide our thinking about potential project locations and in places that we want to spend more time and investing in making improvements for pedestrians. But still, even with that demand map, we know that there could be still additional improvements. We feel like it's been a very helpful tool, but we know that there are always ways to advance it and think forward. And one of the ways in which we are really excited to continue to explore and to think about is around pedestrian modeling, essentially thinking about the routes that pedestrians are taking to get to different destinations and get more granular detail about understanding if pedestrians are walking on one side of a street versus another side, which crosswalk are they using more than others. MIT recently released a preliminary model that they've been working on for New York City. We helped provide some of our pedestrian count data to help as part of that initial calibration of their model. And we're really excited to continue to explore and think about ways in which we can maybe include pedestrian modeling in a future update of our demand map.
Okay, great. Thank you, Esteban. This is great. Next, we're going to have Lisa from MTA present about buses. And the whole point of this is maybe we can collaborate and have our data, what DOT collects, what MTA collects, and how we can have data correlate and help each other out. But Lisa, take it away. She's going to present on buses.
Yeah, hi everybody. I'm Lisa. I manage MTA's Open Data program, and I'm just going to highlight a couple of the really cool bus data sets that we share on the New York State Open Data portal. So I know we have a lot of New York City staff members in the audience. The MTA shares our data through the New York State Open Data portal. That's data.ny.gov. And we'll be putting links in the chat throughout this of the data sets that I'm highlighting. So one data set that I want to highlight that we published a couple of years ago is our bus route segment speeds data set. This has actually been featured in a few presentations already in Open Data Week. So I'll give the very quick version of this, and Jaspreet has put in the chat the link to these data sets. This data is owned by New York City Transit and MTA Bus Company. I won't get into the historic reasons why there are 2 companies that manage buses at the MTA. You can read about it on Wikipedia if you want to learn more. But these data sets provide data on how fast buses are moving between major stops on a bus route for every route in the system. So these major stops on a route we call time points, and these are key operational points on bus routes, and they're what as a rider in our system on the published schedules of scheduled arrival times. So this data set provides the average speed in miles per hour between pairs of time points, the average travel time in minutes, the road distance in miles, and the number of bus trips for each bus route aggregated by month, day of week, and hour of day. In other words, one record in this data set is representing, say, Wednesdays in January at 11 a.m. This data is collected by using GPS bus pings, which determine when each bus is at a major stop along its route, and it's updated automatically every month. So the MTA operates over 6,000 buses, of which over 4,000 run in service every given day. Using bus time, which logs where a bus is every 30 seconds through a GPS ping, we can use an algorithm to determine which route the bus was serving, and from that can determine how quickly buses are moving across that route or between specific stops or time points. So Jaspreet will put a link in the chat to a blog post written by my colleague Yuan, who did a lot of the work to build this algorithm and has talked about the work he did publicly as well. I'd highly recommend reading this if you're really interested in like big data processing and just how bus data works. Users of this speed data should be aware that these calculations include everything that a bus will encounter on its route. So this is things like time the bus dwells to pick up passengers, stoplights, instances where buses change operators mid-route, road closures, maybe a double parked delivery vehicle or traffic slowdowns. All of these we feel are important for representing the true travel time of customers who are riding our buses, and they are what is measured in this data set. So we can see a really simple visual that I built using the in-browser tools on the Open Data portal. Here we're looking at the B35 bus, which runs between Sunset Park and Brownsville in Brooklyn, and we're just looking at the average eastbound times between stops. Looking at this very quick chart we make, we can see, hey, it's interesting that there's one area in this route that looks like speed is like twice as fast as the rest. I wonder why that is, and maybe you want to look into it more. But using this data set alone maybe isn't the most helpful. We designed this data set to be used in conjunction with our bus route and bus stops data set. We'll put links in the chat to these as well. There's an overarching data set for all bus routes. I think it goes back to 2019, and all bus stops back to 2019. And we also created views, which are filtered just for the current route and the current stop, which you can also do with the underlying data set as well. But these are geospatial data sets that contain the polyline and point geometries for MTA bus routes and stops. The stops data set provides details such as whether the stop is a revenue or time point stop, whether the stop allows for boarding or alighting, and whether the stop is within Manhattan's central business district in case you want to easily pull out stops that were affected by congestion pricing. So these data sets are derived from MTA's GTFS feeds and are updated whenever a new schedule is published. Generally, this is about once a quarter. So yeah, if you combine our geometries with the speed data, you can make really cool data sets or visuals like the one we have here. Here we're just looking at the local M1 bus southbound in January 2026. And you could see the different segments within the M1 that appear in the segment speed data set, as well as how quickly those buses are moving, pulled on top of the map of Manhattan. We did do a session on this yesterday where we went really in detail about how you can build this yourself. And we have a Jupyter notebook that is linked in the chat in case you want to play around with that. But the session, of course, is recorded, and once it's posted, you could check it out there because we did move very quickly. So I imagine most people will want, if you actually want to work through it, it might be better to go back to the recording.
Thank you, Lisa. Next, we have Jaspreet that will present on the subways.
Hi, everyone. I'm Jaspreet, and I'm an intern on the Open Data team here at the MTA, and I'll be going over some really interesting subway data sets. So the MTA subway system is one of the largest and busiest public transit networks in the world, and it serves millions of riders across NYC every single day. It operates 24/7. It has about 28 routes running across 36 lines with 427 stations. And you'll soon see that the data owner for most of these subway data sets that we'll present is New York City Transit, which is the agency that handles subway operations as well as other things at the MTA. So the first dataset is the subway hourly ridership dataset, which provides subway ridership estimates on an hourly basis by subway station complex and class of fare payment. The underlying data here is collected from rider entries when someone enters at a turnstile using Omni or using their Metro, and we update this data weekly. We have visualized this data by payment method, where the payment method is either Omni or MetroCard, and this data is aggregated to the monthly level. Some of you may know that the MetroCard is now retired, so with this visualization, we can easily see that January 24, 2024 is when the MetroCard and Omni usage leveled out. From there, Omni clearly took over, and we see people swiping in with the MetroCard much less. We can see this second visualization for the same data set, which begins in January 2024, which again is when the MetroCard and Omni usage levels out. Here we can see how much more popular the usage for Omni became. Some notes about the visual itself: we aggregated the data to monthly totals and filtered it out to include data from 2024 to 2026. And we also applied a 3-month rolling average, which smooths out some short-term fluctuations in ridership, such as weekday seasonality, holidays, and weather-related variability. This next dataset is the subway schedules dataset, which is another NYCT dataset that includes data for both base and supplemental schedules in effect. It includes data on each schedule stop for a given route or trip. The underlying data is provided by New York City Transit's Division of Operations Planning, who generate the base schedules for normal service and then also generate supplemental schedules for construction, maintenance, holidays, or special circumstances such as snowstorms. This data is updated daily, and I do want to make a note that this data is best for analytics since it shows past data. If you're a developer or need extremely up-to-date data for the present and future, it's best to look at GTSS data. This chart shows how often trains arrive on each subway line during weekday rush hours. So instead of showing a single average, it shows the full distribution of wait times between trains. Each horizontal band represents a different subway line, as shown by the y-axis, and the x-axis shows the number of minutes between trains. So moving left means more frequent service, and moving right means longer wait times. The shape of each band shows how common different wait times are. So taller or wider parts mean that the wait time happens more often. You'll notice that lines like the 7 and the L stand out with the curves that are farther to the left and are more tightly clustered. This means that the trains are arriving more frequently and more consistently. And the reason for that is that these lines use communication-based train control, CDTC, which is a signaling system that allows trains to continuously communicate their positions, allowing them to run closer together in a more safe manner, and also adjust in real time, which reduces wait times and improves the reliability of these trains.
Okay, thank you, Jaspreet. That was very interesting. Very cool graphics and charts. Okay, so next up we have Alec Bardey that will present on traffic counting and modernization of counting vehicles.
Thanks. Hi, everyone. I'm Alec. I'm a data lead in regional and strategic planning in transportation planning and management at the Department of Transportation. And yeah, as mentioned, talking today about traffic counting and modernization efforts with computer vision. So to set the context here, as an agency, we collect a lot of data. Esteban already elucidated eloquently the utility of pedestrian counts, but we collect weigh in motion data, we collect ATR, automated traffic recorders, that's like sort of bin traffic counts, biking and micromobility counts, and vehicle classification counts, among others. Today we're going to be focused on VCC, or vehicle classification counts. So a little bit about vehicle classification counts. Right now, the processing of these counts is slow and prohibitively expensive. And so the way that this is conducted is we go out, we have a contractor set up a camera that records 24 or 48 hours of traffic footage. And then that footage is set off to another subcontractor who then manually counts that footage. So it's a costly and timely or slow process, and it's not particularly timely, where, about 80% of the total cost associated with it is associated with the actual manually counting and reviewing of the footage. Only 20% is associated with the storing of the data and the setting up of the cameras. What this sort of represents is actually an interesting opportunity where we have 15 years of video footage and then associated counts. So it's really an opportunity, a really good opportunity for innovation. And that's where this project steps in. So yeah, how are we modernizing? And so what we're doing is we're implementing a computer vision traffic counting prototype via a YOLO model. This is a project that's led by New York Metropolitan Transportation Council fellow and PhD candidate Bushra Khalili, who is, I think, in the chat. So I'm really just the face for this project. I think she's really the brains and the muscle behind it. But yeah, I'm not going to explain so much, get into the weeds about like computer vision methodologically, but in effect, it is turning pixels into numbers, and then the computer is like learning from those numbers in order to make like classifications, draw bounding boxes, and draw inferences from images in order to identify and track objects across a moving image. So we're going to jump right into a video prototype. This is what the model looks like right now, where we have a video, as you can see, on a busy road, an interstate, and we are classifying vehicles as they are going both in and out across this white line, where that white line is the threshold. And you can see the sort of like classification tag associated with each of the vehicles around the bounding box. Cool.
Very cool.
Where we're at right now is a prototype, but the sort of next stages are to scale this into a functional tool. And there are a lot of challenges associated with scaling this into a tool that can be used across the agency. Mainly, within the agency, the VCC counts, the vehicle classification counts, are disparately stored and poorly formatted. So this is a screenshot of what those counts look like, where you have this sort of weird header, you have merged cells. And so if you're like a data person, this is not like a particularly friendly format for you to like aggregate counts and be able to do high level aggregate evaluations. And on top, that's compounded by the fact that this format changes over years and over contractors. Since we have 15 years of data, there's a lot of inconsistencies. So one key part of this project that is like concurrent to the computer vision work is to generate scalable ground truth data. So turning those individual Excel files into effectively a database. And so this is like a DAG chart for what that process looks like, where we are generating a list of all of the VCC files, the vehicle classification files over the last 15 years, and then establishing a mechanism to identify all these different formats, clean them, standardize them, and then centralize them into a database that eventually would be accessible, not just for this project, but across the agency, and then eventually published on open data. And then, tying back to the computer vision work and thinking about this as a functional tool. So once we are past the stage of evaluation at scale, we want this to be something that is an interface for people across the agency, for planners and analysts who want to be able to generate their own counts from existing video data. And so we have a couple screenshots here of what that interface looks like. This first one is just like the layout on a map where you could basically upload the link to the video. It would populate in accordance with a backend like database that connects a segment with the latitude and longitude. And so you would be able to see where your video is as a point on the map. And then here on the left side, there's like a variety of settings that sort of dictate model speed and how the videos are split up on the back end side. And then the next stage allows the user to select that threshold. So as you saw in the video, there was that white line that determined the ins and outs of the classification counts. And so this would be the point in the interface that would allow the user to select that threshold in case they only wanted one side of the street, or if there was a particular part of the video where that sort of threshold was ripe for counting, for example. And then this is just like the output page where you're seeing that processing on the back end. Because we have these 24-hour video counts, we're splitting these videos up into smaller bite-sized segments for the model to be able to digest. And then also that leads to a potential for parallelization, where on the back end, we can generate inferences on a lot of different videos at once. And then, to connect these dots, talk about the sort of final data product. I think we see this as both a short-term and a long-term data product, where in the short term, we have this vehicle classification count pipeline that is generating analysis-ready data that will be published on open data, that'll be usable for people across the agency, because we don't have that as an agency right now. We just have those individual Excel files. But then in the long term, using this computer vision model in conjunction with that now like scalable and analysis-ready ground truth data to bolster existing data, bolster the video classification data. And I think we see that in a couple different ways, both by saving the agency money. As we mentioned, like 80% of the cost associated with those counts is from manual review. So if we're able to save the agency money, we can do more counts, we can cover more of the city and collect more data. But then also to be able to generate counts from existing footage. We have 15 years worth of recorded videos, and oftentimes a count will be for one particular purpose. So we'll do a count and we're counting like trucks, for example. And so we could revisit a lot of that old data and generate pedestrian counts, generate bike counts in those old video footage. So this is just like a snapshot of what the data looks like in its unstructured format, what it will look like. And that's everything.
This is great. Thank you, Alec. And just so you know, this is the top is what we have now. And I believe that format is not acceptable or accepted for open data purposes. We have actually somebody in the agency recreates it to the format below, so it could be accepted on the portal. So automating this process will be great. And like you said, it will save the agency resources. All right. Thank you so much. And then next we have Lisa from MTA that will continue the presentation and the conversation on vehicles.
Thanks, Alec. So I think one of the biggest topics in vehicle movement in New York City over the past few years has been congestion pricing. I saw a comment in the chat asking about congestion pricing as well, so we are going to talk about that next. So in case you missed it, vehicles are now being told to enter the congestion relief zone in Manhattan. These are local streets and avenues at or below 60th Street, and this program is administered by the MTA. I think one of the coolest things about this program, besides the toll itself and the immense impact it's had, is that open data has been at the center of how MTA reports on the program. So not only does the MTA use open data like the city's 311 data to measure things like a 70% drop in excessive honking reports, we've also been publishing data sets on the program since the month it launched in January 2025. So we'll briefly go over one of my favorite data sets from this program, which is congestion relief zone vehicle entries, and we'll drop a link in the chat to this. So this data is owned by MTA Bridges and Tunnels, who administers the program, and the data set provides the number of crossings into the congestion relief zone by different locations and vehicle class in 10-minute intervals. This data is sourced from the roadside tolling system. These entries are available since the start of the tolling program on January 5th, 2025. An entry in this data set refers to a single instance of a vehicle crossing the boundary into Manhattan, south of and including 60th Street during a trip, and this data set updates automatically weekly. So I think there was a comment in the chat earlier about real-time data. This is from tolling data. It takes a while to process. It's not real-time, but there are companies out there that do real-time traffic APIs. Like, I think here is one. I think there's different like cell phone data that you can get that approximates traffic, but this is after the fact tolling data. You can see a cool chart that's been made using this data, which I will not take credit for. This was all done by other data science teams at the MTA who worked very late hours once the program was told it was turning back on and in the months after that. But I think this line chart that they made is a really cool example of very clear behavior change from the program. Because this data is at the 10-minute interval, you can see just before 5 a.m. people rushing to get into the congestion relief zone before the toll goes into effect, and then a very quick drop right at 5 a.m. when the toll turns on of people who just avoided it or are going to just wait till a later time in the morning to make their commute. And then here you can also see that peak hour of the 7 a.m. roughly of when people are crossing the Lincoln Tunnel. You can read more about this data set and how it got put together and look at some fun charts like these in a MTA data blog post that was written about this by the team who worked on this data. Would highly recommend checking that out if you want to know more about how this data set works. All right, and then I think not many people know that the MTA also manages the tolling on many bridges and tunnels in the New York City area as well. So this data set was created by my colleague, Nikki, who worked really hard on getting this data from a very difficult data source, and now it updates weekly for you all to use. This provides hourly bridge and tunnels crossings by facility, direction, vehicle class, and payment method. It's a count of all traffic on the facilities, regardless of whether the driver ultimately pays the toll. Now, I think this is one of the most detailed data sources we have about traffic in just the New York City region broadly and how people are moving, especially with that direction and vehicle class field. This data in this data set is based on a preliminary assessment of electronic tolling data read at the time of the vehicle crossing. So it uses this technology called automated vehicle classification technology to determine the vehicle class, and it also estimates whether someone's going to pay with EasyPass versus tolls by mail based on whether there is a transponder for EasyPass in the vehicle. And then we can see another quick chart that I created using the in-browser visualization tools offered by the Open Data Portal, which I'm a big fan of people using just to play around with and pull quick insights from data. So here we're just looking at passenger car traffic over the Verrazano Bridge. I pulled a random week in November 2025, but I'll leave people with the idea that you could look at this data for the day of the New York City Marathon or other days where there are big road closures and see some interesting stuff. But yeah, I love looking at any peak hour analysis with our hourly data, whether it's subway or bus ridership or this hourly crossings data set, because you begin to very clearly see trends of when people are traveling and allows you to just better understand mobility in the city overall. And with that, I'll pass it back to Hong. Thanks.
Thank you, Lisa. And last but not least, we're going to have Mark present on the Citywide Mobility Survey, which we have just presented different ways of people traveling and use different methods of travel. So we are not limited just to buses and trains. So we do a survey that will show trends of mobility throughout the city. So take it away.
Thank you, Hong. Hi, my name is Mark Seaman. I head the economics and analysis team in the policy unit in DOT's commissioner's office. A lot of our work depends on having good quality data on transportation. One of our richest data sources is the Citywide Mobility Survey, which we also happen to manage. And so I'll tell you a little bit about what the survey is about, how we collect the data. I'll show you a few high-level results to give you a taste of about what the data is that we collect, and then I'll finish with 3 more involved analyses we've done using the data set. So the Citywide Mobility Survey, or CMS as we call it, is a household travel survey that we conduct every 2 to 3 years from a sample of New Yorkers to understand how people get around the city. We collect really detailed information about how people use transportation in the city. It helps us understand baseline transportation conditions. We can see how travel behavior changes over time. We can see how behavior varies across the city and by demographic groups, and it helps us understand gaps in equity. We carry out the survey by sending out a huge number of invitations in the mail. We offer respondents a small incentive to participate. Most respondents download an app onto their phone that allows us to collect 7 days of travel data, but we also allow for respondents to take a web-based survey or even take the survey by phone interview, in which case we collect 1 day of travel data. The smartphone app, if you download that, it records a GPS trace of the participant's travel, and it organizes it into trip records that are reviews with the participant at the end of the day. You can see an example here on the right. The app guesses which mode or modes were used and allows the user to edit that to fix any errors. It asks the purpose of the trip, and it collects lots of other details like whether the trip was with another household member, and it collects lots of mode-specific details if you're Our 2024 survey collected results from 3,500 participants. Each of our surveys has had around 3,000 participants, captured data on over 100,000 trips. All of that was in May and June of 2024. And so to give you a sense of what the data is that we're collecting, I'll walk you through three very, very simple analyses of the data. So our signature metric, not available anywhere else, is mode share on all trips. So if you consider the main mode for a trip, that's what we're showing here. If you take the subway somewhere, but you walk to and from the stations, we count that as a subway trip. We ignore the walk trip portions for that purpose. We're not throwing out walk trips in the data, but for this purpose of calculating the main mode share, we're looking at what the main mode for the trip was. So in that case, it's a subway trip. And what you can see here is even with that, walking and driving are pretty much tied in 2024 for the most common mode that is used within the city by New Yorkers. Walking has increased slightly since 2019. Transit, as we all know, we can see that here, dropped from 2019 to 2022 as a result of the pandemic and has recovered partially. Biking has increased a tiny little percent in the overall scheme of things, but as a share of bike trips is actually pretty notable increase. We also collect data on deliveries of all kinds that participants receive every day that participants take the survey. We ask them about deliveries at their household. 41% of New York City households receive a delivery on a typical day. That's up from 31% in 2019. And that's any kind of delivery. And you can drill down further and look at the typical household deliveries of packages or takeout or prepared food from restaurants or from grocery store and so on. And most of these categories have increased significantly since 2019. We also ask about open streets. Since 2020, DOT has worked with communities across the city to create open streets that are open to pedestrians and not vehicles, sometimes for a few hours, for a few days per week, sometimes much more. We asked about their respondents' familiarity with open streets, and you can see there's a wide variation across the city, probably related to where open streets are most common. So in the Manhattan core, people who live in Manhattan core are most familiar with open streets, and in outer Queens, outer Brooklyn, they're least familiar with them. And then, so I want to now give you a sense of the kind of rich analyses that you can do with the citywide mobility survey. We're linking across tables. The citywide mobility survey data set is several tables that you can knit together in code. So I'm going to give you some examples of these and of how we've used the data at DOT. We have this question: where are people parking on the street, in which parts of the city? If we were interested in, say, understanding where people cruise for parking, or where should we think about putting on-street electric vehicle charging, this kind of information could be really helpful. Next, move forward. So it turns out we have a very handy question in the survey that helps us with this. We ask people where they typically park their vehicle when they're parking at home. Is it on the street? Is it in their garage or driveway or shared driveway? Is it in a garage or is it in a parking garage or a parking lot? We obviously only ask this of people who own cars, which is about half of the city. We can see the responses across the city here, colored by where people park. So red is where people are parking mostly on street. Yellow is where the participants said that they are parking their own driveway or garage, and green is where they're parking in a separate garage or lot. So if we want to focus on just where the zones where people are parking on the street, so move forward, then let's move forward again. We can actually see aggregated at the zone level. We can see where on-street parking dominates. You can see that the inner Brooklyn zone is where the highest percentage of households who have vehicles are parking on the street. Upper Manhattan and Southern Bronx also have really high shares of people who are parking on the street. So for our next question, we wanted to estimate where new bike trips come from. We're interested in this because we wanted to understand the greenhouse gas impacts of new bike trips. If people are shifting from walking or transit, that's not having an impact on greenhouse gases. But if we're moving people out of a vehicle, then it could. So if we want to estimate this, what the concept that we use is, let's look at trips that are the same distance as bike trips, and we assume that bike trips are replacing modes that are also commonly used for those distances. Bike trips tend to be 1.5 to 2 miles long. That's the average, but of course there's a distribution across the whole range of distances. With the citywide mobility survey, we can look at the few thousand bike trips that we recorded. We can see the distribution of distances, and then we can look at all trips that we recorded. And earlier I showed mode share for all trips. Here we're looking at mode share by distance band, and we can apply these numbers to the distribution and so what you see here is shortest distance, walking dominates. And then as the trips get longer, there are fewer and fewer walk trips, and we get more transit and vehicle trips. And using this, we can figure out that if we look at it citywide, if we tried estimating this citywide, we would say 36% of bike trips would have been taken by car. And we think probably looking at Manhattan is more reasonable, where there's much more bike infrastructure. And if we do the analysis for Manhattan, we get 15% of trips would have replaced car trips. The most extensive application of citywide mobility survey data has been development of a pedestrian route choice model to help us understand the attributes of streets that are most valuable to New Yorkers. We took 17,000 walk trips from the 2019 CMS. For each trip, we used the GPS pings to determine the actual route taken. So we've shown an example of that here on the right, where we've matched the GPS pings. We estimated other routes that could have been taken, sometimes shorter, sometimes longer. We collected attributes for each route, such as distance, traffic volume, sidewalk and street width, land use, trees, whether there are street lights, scaffolding, crime levels. And then we estimated with all of this, we put it all into a big statistical model, and we estimated how much New Yorkers go out of their way for each attribute. And essentially, that tells us how New Yorkers value each one of these attributes. This actually formed the basis of a PhD dissertation by a graduate student who is working with us, and we plan to publish the results. I've shown you a little bit about how you can use the richness of the citywide mobility survey to answer questions. We encourage you to explore the data sets to see how they can advance your own work. Hong mentioned we just today, with her help, posted the 2024 data to open data. We'll be updating DOT's website to point you there also, and to point you to our user guide with tips for advanced data users. That's it.
Okay.
Thanks.
Great. Thank you, Mark. So thank you, everyone. We have some of the data sets that were discussed during the presentation listed here. Feel free to browse. The Open Data Portal has, like Tara said, thousands of data sets, and it's really interesting to look through. I know we're short on time, but I know Lisa was looking in the chat, monitoring the chat for questions.
Yeah, maybe we have time for just one question.
Oh, yes.
There's one question in the chat for DOT about just if you guys have any theories about why pedestrian counts have struggled to recover since 2020. Are people using other forms of mobility, or are their routes shifting?
That's a really interesting question. I think something that we are wanting to look at more. And I think to Mark's presentation about the citywide mobility study, we are seeing all different types of changes in people's travel behavior. People are getting a lot more deliveries. So maybe they are walking to certain commercial areas less. So yeah, definitely something that we are wanting to continue to explore and think about. But yeah, and wanting to look at all different types of data sets to get like a fuller picture of how travel has changed a lot since the pandemic.
Yeah, and I can add to that. What we've seen with the citywide mobility survey is that overall travel has declined. We've certainly seen a drop in transit trips as well. Remote work has certainly been a big part of that, is that if there are fewer trips to the subway or bus or commuter rail, then there are also fewer walk trips to and from those, and then fewer walk trips from your workplace, maybe to go out and get lunch or whatever. As a share of trips, walking is actually holding pretty steady. And then to Esteban's point about deliveries, the increase in deliveries is certainly affecting things. And what if we look at trip purpose, the purpose of trips, there's been a sharp drop in shopping trips. And so there's very likely replacement of shopping trips with online shopping.
That's good. Thank you. So if you would like to contact us, feel free to go onto the contact us page on the open data portal. The questions will actually go to their respective agencies. We can address there. Thank you. Have a great day, sir. Bye.